Hi, my name is John Lee. I'll be telling you about the Rankine cycle as the reporter last week, or for this week. So just an introduction. So the Rankine cycle is a thermodynamic process. So in general, we need to know about thermodynamics. So thermodynamics is the study of the energy and how do you convert this energy from heat into useful work. So in the beginning, Scottish civil engineer William Rankine actually was the founder of some of the basic thermodynamic principles. And he actually developed a thermodynamic process called the Rankine cycle. This cycle is a theoretical process that is used in most of the world's power production. And our objective in this experiment is to go ahead and we're going to talk about the understanding the Rankine cycle, and then we're going to measure the relevant data that was described in the experiment. Then we're going to calculate the associated parameters that are important to the Rankine cycle that give the performance of it. So the theory of the Rankine cycle is that it converts mechanical power into electrical power using these simple things here. You use a pump to pump the water into high pressure. This goes into the boiler, and then this boiler heats the water. The water is then sent to the turbine, or through a nozzle first, to accelerate the speed of the steam. The steam goes to the turbine and creates power by decreasing the kinetic energy of the steam. This steam then goes to a condenser and is cooled down, and it is brought back through the pump, and then the cycle starts over again. And this is just a picture representation of this Rankine cycle. As you can see here, this is some more theory on it. You have the pressure versus specific volume graph, which just shows 1 to 2 where it's being pumped, and then 2 to 3 is the boiler, 3 to 4 is the turbine, and 4 to 1 will be the condenser. And you can also see in terms of entropy on the right. This is our experimental apparatus. Some of the things that you want to kind of take note of is going to be the data acquisition system, which is going to be the computer on the left. Then we have our condenser tower, that's the gold piece. We'll have our turbine as well as our boiler over on the right, and we'll have our heat source, which is going to be our propane. So to start up the system, we're going to go ahead and turn all the valves off, all the switches off, and make sure that the power is in minimum position. Then we're going to make sure that the condenser tower is drained of water, but this is something we did not do. We actually had some wrong values there. Then we're going to make sure that we have the water is put into the system, and we'll make sure that the DAC is connected to the computer. Then we'll make sure that everything is properly connected. Continuing, we also need to make sure that the computer is turned on, that the fuel source is turned on, that all these other switches are on, and then that we have the combustion blower come on within 45 seconds. And we need to preheat the system about 7 to 10 minutes and then drain the condenser again. So furthermore, we also have to make sure that the temperature is reached in the boiler about 175 degrees Celsius. And then we reach about 110 psi in the system. We're going to try to adjust our load to get the proper system set up, so we have a steady state area that we're trying to get to. And then we're going to indicate our water level, and then we'll continue here with our measurements. We're going to run this experiment about 10 to 15 minutes, and then we're going to drain the system and record the volume. And then we allow the system to cool, and then make sure that the pressures decrease, and then we can remove our amount of water from the reservoir. So next we log the data, and we save this data into an Excel file, and then I'm going to explain a little bit more about that in just a moment. So just furthermore, with the shutdown, we're going to make sure that we turn off all these switches and leave the steam emission valve in the full open position to make sure that we don't have any flow going through. So the data reduction that I did, I went through and plotted all these different ideas in terms of time. And as you'll see in some of these graphs, I went through and marked the steady state. I assumed between about 180 seconds to about 600 seconds is where I assumed that it was about steady state if you look at some of the graphs. And then at 400 seconds is where I actually said, this is where I'm going to do a little bit of analysis. So as we're going through here, you can see the boiler temperature versus time, and my point at 400 degrees Celsius, 400 seconds. Furthermore, the boiler pressure versus time, turbine inlet over outlet pressure versus time, and the temperature, the amount of AC amps that we created, DC amps that we created, the DC volts, the turbine RPM versus time. And then when I went through, these are some of the amounts that I calculated or found from the computer program. You can see where we have the different pressure, the amount of initial fill amount that we had in the boiler, all the different pressures and temperatures associated with each one of the components. And then we have our amount of 0.81 liters, which is actually, should be wrong. It should be about 250 milliliters instead of 810. So when I used the thermodynamic tables, I found that we had a heat flow out of the boiler of about 7.5 kilowatts. The heat flow of the fuel, which is about 2,335 kilowatts. So there's not really much heat going into the system. That's being actually converted into heat of the steam in terms of how much we actually put in with the fuel. We got about 84 watts from the turbine, and the efficiency of the generator turned out to be about 5%. This is because we got about, I think it was like 4 watts whenever we actually did it. So then we've got these different numbers here. We have a system mass flow rate of about 0.00369 kilograms per second, and our overall efficiency for the system was about 9%, which seems a little bit low because most of the time you hear about 20 to 30% should be for the value there. Some possible errors that we could have had with our system is that we may not have actually been in steady state, we just kind of assumed it. We could have had low load on the system, on the generator, and this could have caused us to have really low output of power. We could have had impure steam going into the turbine, and this kind of gives you like the kicks where you just have like a sputter of the system, and it's like water hitting the turbine and it's not creating as much power at that point. Then we also have the digital readout of about half a watt compared to on the computer it said about 0.8 watts. This is about 100% error if you assume that the analog is correct. Some additional comments, just to talk about the kicks again. We allowed the system about 5 to 10 minutes to warm up, and then it's still fluctuating through the experiment. The thermal efficiency was also low, and as I said earlier, it can be increased by reducing the heat input. Yes. And let's see. And these are the references that I used. That's it. Thank you.
Any questions?